They are standing in a river. The water is moving against them. Somewhere on the other bank, there are people trying to kill them. And their job, the reason they are standing in that river at that exact moment, is to build a bridge. Not after the shooting stops. Not once the area is secured. Right now, while the rounds are coming in, while the mortars are walking toward their position, while their teammates are taking cover, and the radio is screaming with traffic, and the far bank is lit up with muzzle flash. They are building a bridge. And when it is done, when those first tanks roll across the structure, these men built under fire in the dark, with their hands shaking and their ears ringing, the entire battle changes. The front line moves. The momentum shifts. The enemy position collapses. All because a small group of soldiers decided that the obstacle in front of them was not a reason to stop. It was a problem to solve. These are combat engineers, and what they do is one of the most dangerous, most physically demanding, most technically complex jobs in the entire military. Most people have never heard of them. Most people do not know their names. Most people do not understand that without these soldiers, without their bridges and their boats and their explosives and their raw willingness to work in the kill zone so that everyone else can pass through it, modern warfare as we know it would grind to a complete and total halt. Before we go any further, take 1 second right now to subscribe. Over 98% of people watching this video have not subscribed. It costs you nothing. It takes 2 seconds, and it means you will never miss a story like this one. Hit that button now, and let us get into it. The history of military bridging is almost as old as war itself. Armies have been crossing rivers to fight each other since before written records existed. The Persians bridged the Hellespont. The Romans built pontoon bridges across the Rhine and the Danube with such precision and speed that their enemies considered it a form of military sorcery. Julius Caesar once built a bridge across the Rhine in 10 days, crossed it with his legions, demonstrated Roman power to the Germanic tribes on the far bank, then marched back and destroyed the bridge behind him. He built it not because he needed to stay. He built it to make a point. That is what military bridging has always been. It is not just engineering. It is a statement. It says we are coming, and nothing you put in our way will stop us. Fast forward 2,000 years, and the stakes are exactly the same. The technology has changed. The urgency has not. The danger has not. And the men doing the work have not changed in the ways that matter most. They are still standing in rivers. They are still working under fire. They are still solving the unsolvable problem on a timeline that would make any civilian engineer go pale. Let us start from the beginning. Let us talk about who these people actually are. Because before you can understand what combat engineers do, you have to understand what they are made of. A combat engineer in the United States Army enters service through one of the most grueling pipeline training programs in the military. They complete basic combat training alongside every other soldier, but then they go to Fort Leonard Wood in Missouri, and that is where things get serious. Engineer school is where these soldiers learn the full spectrum of what their job demands. They learn how to construct fighting positions, how to breach minefields, how to detect and disarm improvised explosive devices, how to demolish enemy structures, how to build assault bridges, how to operate heavy equipment under combat conditions, and how to survive in an environment where everything around them is designed to kill them. These are not soldiers who specialize in one narrow skill. They are expected to be fighters first and engineers second, or depending on how you look at it, engineers first and fighters always. They carry rifles. They pull security. They fight alongside infantry. And then, while the infantry is holding the line, the engineers move forward and build the thing that allows the fight to keep going. The unofficial motto that runs through the engineer community is a phrase that gets repeated in training, in the field, and in the quiet moments after a mission when everyone is still processing what they just did. Essayons. It is French. It means let us try. It was adopted by the Army Corps of Engineers in 1813, and it has never stopped being true. When the obstacle is impossible, when the conditions are impossible, when the timeline is impossible, the engineer looks at all of it and says, let us try, and then he gets to work. Now let us talk about water, because water is the obstacle that has defined military engineering more than any other single feature on the battlefield. Rivers, lakes, canals, flooded plains, swollen creek beds turned into 20-foot wide rushing channels overnight. Water stops armies. It always has. And the side that figures out how to cross it first, and how to keep crossing it, almost always wins. There is a reason that in military planning, water obstacles are called gap crossings, because that is what they are. A a gap in the terrain. And gaps cannot be exploited. They cannot be flanked, they cannot be suppressed or destroyed. They can only be crossed, and crossing them means either building something or using something that can carry soldiers and vehicles from one bank to the other, while the enemy does everything in his power to make sure that does not happen. This is where the assault bridge comes in, and this is where combat engineers earn everything that has ever been said about them. An assault river crossing operation in the United States military is one of the most complex and dangerous combined arms operations that exists. It involves infantry, armor, artillery, aviation, engineers, and command and control elements all working in precise coordination across a contested waterway, with rounds coming in from multiple directions and no margin for error on the timing. Here is how it works. Before a single bridge section enters the water, the engineers have been doing reconnaissance for hours, sometimes days. They need to know the river's width. They need to know the depth at multiple points. They need to know the current speed and direction. They need to know the composition of the bottom, whether it is sand or rock or soft mud that will swallow a vehicle the moment it tries to cross. They need to know the condition of the banks on both sides, whether they are accessible to heavy vehicles or whether they are steep and reinforced and will require their own engineering solution just to get to the waterline. All of this information is gathered by small teams of engineers who go forward, often at night, often without fire support immediately available, and they get into the water. They swim it, they probe it with poles, they take readings, they sketch the crossing site, and then they come back and brief the commander on exactly what they found. This process alone, the reconnaissance, requires extraordinary personal courage, because the enemy knows that river matters. The enemy knows that if they can stop a crossing there, they can hold the entire offensive. So the far bank is watched, it is defended, it is potentially mined, and the engineers who go into that water to take measurements are fully aware that if they are spotted, if they make a single sound that carries across the water on a quiet night, the situation changes instantly. After reconnaissance comes planning, and the planning for an assault river crossing is extraordinarily detailed. The engineers have to determine which crossing technique they will use, based on what the reconnaissance showed them. They have to coordinate with artillery to suppress the far bank during the crossing. They have to coordinate with aviation to provide observation and security. They have to sequence the crossing so that the first elements across, who are inevitably the most exposed, have just enough support to survive long enough for more to follow. And then they have to build the bridge while all of that is happening around them. Let us talk about the equipment, because this is where the technical side of what engineers do becomes almost hard to believe. The primary bridging system used by United States Army combat engineers for decades was the M4T6, and later the improved ribbon bridge, commonly called the IRB. The ribbon bridge is a floating bridge system made up of modular sections called bays that can be connected end to end to span a river of virtually any practical military width. Each bay folds up for transport on a specialized carrier vehicle called a bridge erection boat carrier. The boat itself, the Bridge Erection Boat, or BEB, is a powerful watercraft that the engineers use both to push bridge bays into position and to hold the completed bridge in place against the current once it is assembled. Here is the remarkable thing about the ribbon bridge system. A trained engineer crew can take a bay off the transport vehicle, unfold it on the water, connect it to the previous bay, and move on to the next one with a speed that seems impossible for the scale of what they are doing. Under training conditions with experienced crews working together, a ribbon bridge capable of supporting main battle tanks can be completed across a river of significant width in under an hour. Under combat conditions, with incoming fire, with people wounded, with equipment damaged, with the river pushing against everything they are trying to build, with the far bank still being contested, that timeline stretches, but it does not stretch indefinitely. Because the engineers know that every minute that bridge is not complete is a minute the infantry on the far bank is taking casualties without reinforcement. Every minute that bridge is not complete is a minute the mission is failing, and that knowledge drives them with a force that no training schedule can fully replicate. The bridge erection boats are crewed while the bridge is being built. That means there are engineers sitting in those boats exposed, in the water, in the middle of the crossing site, holding the bridge in place and maneuvering bay sections into position, while rounds are impacting around them. You cannot do that job from cover. You cannot do that job from concealment. You are out there in the open water doing work with your hands that requires both hands, and you stay there until the bridge is done or you are physically unable to continue. There is a particular kind of courage that the engineer community talks about that is distinct from the courage of infantry soldiers moving forward under fire toward an enemy. That courage is very real, and it commands total respect. But there is something additionally demanding about the courage required to stay still under fire and keep working. To not move, to not take cover, to not run, to hold your position and continue a technical task that requires focus and precision, while every instinct in your body is screaming at you to get low and get away. That is the courage of the combat engineer building a bridge in a contested crossing site, and it is its own category of extraordinary. The assault river crossing does not begin with the bridge. It begins with the far bank, and taking the far bank is the infantry's job, done in boats while the engineers are still preparing the bridge. The initial crossing element, usually infantry soldiers in assault boats, crosses the river before any bridge exists. They go in the dark, in the noise, with whatever fire support can be arranged, and they establish a toehold on the far shore, a beachhead, a small piece of contested ground that the engineers are going to need to exist for their bridge to have anywhere to land on the other side. Those assault boats are operated by engineers. The combat engineer soldiers manning those boats are driving into enemy fire, delivering infantry to a bank that is actively being defended, and then circling back to bring the next wave. They do this repeatedly. They do this while taking fire. They do this while watching soldiers they just carried across get hit before they even reach the tree line on the far bank, and they go back. That is not abstract courage. That is a very specific, very deliberate decision made in real time to keep doing something that is visibly and immediately getting people killed. Because if they stop, the infantry on that bank is alone. And if the infantry is alone on that bank, the crossing fails. And if the crossing fails, the mission fails. The engineer gets back in the boat. Now let us talk about what the enemy does while all of this is happening. Because the enemy is not passive. The enemy knows that a bridge is the most dangerous thing that can happen to their position. A defended river is a powerful force multiplier. As long as the river is a barrier, the defender has the advantage. The moment a bridge goes in, that advantage collapses almost instantly. So the defender will do absolutely everything possible to stop that bridge from being completed. Artillery fires, mortars, anti-aircraft weapons depressed to fire horizontally into the waterline. Machine gun positions dug in on the far bank to cover the crossing site. Snipers positioned to target engineers specifically because removing the engineers removes the bridge capability. Mines placed in the water and on the near bank approach to delay and disorganize the crossing force. Demolitions placed on any existing bridges to deny them to the attacker. Anti-tank guided missiles positioned to engage the bridge erection boat carriers before they even reach the water. This is the environment the combat engineer works in. This is the context in which those bridge bays go into the water. Every hand that reaches for a connector pin between two bay sections is doing so in the knowledge that this crossing site is targeted, that the enemy knows exactly where they are, that there is no concealment for a bridge being built on an open river, and that the only thing between the engineers and the enemy fire is the suppression being provided by friendly artillery and the soldiers on that far bank who are fighting to keep it. Let me tell you about a crossing that defines what these soldiers are capable of. Because history provides the clearest lens for understanding what combat engineering really means. In March of 1945, as Allied forces pushed into the heart of Germany, they faced the Rhine River. The Rhine was the last major natural obstacle between the Allies and the German heartland. Hitler had ordered it defended at all costs. German forces had destroyed every bridge across the Rhine in their retreat to deny it to the advancing Americans. Every bridge except one. The Ludendorff Bridge at Remagen was still standing. It was damaged. It was being prepared for demolition, but it had not yet been blown. And on March 7, 1945, elements of the 9th Armored Division found it intact and crossed it under fire before the Germans could complete its destruction. The bridge held, barely, for 10 days before it finally collapsed from accumulated damage. But those 10 days were enough. American forces poured across, and the engineers, the combat engineers of multiple units, immediately began building additional pontoon bridges at Remagen and at other crossing sites to sustain the flow. Working around the clock in freezing temperatures, under air attack, under artillery fire, under fire from German forces on the far bank, engineer units constructed floating bridges capable of carrying tanks and artillery. They worked in shifts so that the construction never stopped. When men were wounded, others took their places. When equipment was damaged, improvised solutions were found. The bridges went in because the engineers refused to allow any combination of enemy fire, equipment failure, or physical exhaustion to stop them from going in. One first-hand account from an engineer officer during the Rhine crossings described watching his soldiers work under artillery fire that was landing in the river within 100 meters of the bridge site. He wrote that his men did not stop working. They flinched. They took cover momentarily when rounds landed especially close, but they went back to the bridge, every time, and the bridge got done. This is the lineage that modern combat engineers carry. This is what they are trained to meet, and the expectation has not changed since 1945. The Rhine is in the history books, but the rivers are still there, the obstacles are still there, and so are the engineers. Let us move to more recent history, because the lessons of World War II were not the last time American combat engineers proved that a bridge can change the outcome of a battle. During Operation Iraqi Freedom in 2003, the 3rd Infantry Division's advance from Kuwait toward Baghdad was one of the fastest armored movements in military history, and it was made possible, in critical moments, by combat engineers. The Euphrates River presented a significant challenge. Iraqi forces had destroyed or prepared to destroy bridges along the route of advance. At multiple crossing sites, engineer units moved forward under fire, conducted hasty reconnaissance, and either repaired damaged bridge structures or constructed floating bridges to carry the armored columns forward. At the Tallil Air Base area and at other crossing sites along the Euphrates, the images that came back from embedded journalists showed something that does not fit neatly into any civilian understanding of what engineering means. Soldiers in the water, equipment being pushed into place while tracers lit the night sky, bridges going together piece by piece while the sounds of the battle on the far bank carried clearly across the water. The 3rd Division's attack lasted 21 days from Kuwait to Baghdad. In those 21 days, engineer units built or repaired multiple bridges under varying degrees of enemy contact. They cleared routes of mines, they breached obstacles, they kept the armored columns moving when the terrain said stop, and the campaign succeeded in part because of that. Now let us go deeper into the technical side, because understanding what these engineers are actually doing with their hands helps explain why the job is as hard as it is. The modern assault bridge comes in several forms depending on the tactical situation and the type of gap being crossed. The improved ribbon bridge, which we discussed earlier, is the workhorse of wet gap crossings. Wet gap meaning a crossing with water. But engineers also cross dry gaps, anti-tank ditches, destroyed road sections, ravines, craters. For those, the equipment is different. The Armored Vehicle Launched Bridge, or AVLB, is a tank chassis with a scissors bridge mounted on top. The bridge folds open and drops across a gap with no human outside the vehicle at any point during the deployment. The entire operation can be completed in about 2 minutes. It can span gaps up to about 60 feet and carry main battle tanks. It is designed specifically for the situation where speed matters more than anything else, and where keeping the crew inside armor is the difference between life and casualty. The AVLB crew drives to the gap edge under fire. They extend the bridge hydraulically. It unfolds, drops across the gap, locks into position, and the crew drives away, while the tanks cross over them. Then when the crossing is complete, another AVLB or engineer team retrieves the bridge so it can be used again. The whole sequence, from approach to completed crossing, can happen fast enough that the enemy does not have time to react effectively if the timing and suppression are coordinated correctly. There is also the Rapidly Emplaced Bridge System, or REBS, and the Medium Girder Bridge, or MGB, which is a modular panel bridge system that can be constructed by a small team of engineers without heavy equipment to span medium gaps in situations where heavier systems cannot be brought forward. The MGB is the kind of bridge that gets built by hand, panel by panel, section by section, with soldiers carrying components forward to the gap edge and assembling them under whatever conditions exist at that moment. Let me describe what it looks like to build a medium girder bridge under realistic combat conditions, because the technical description does not fully capture the human reality of what this requires. The engineer team arrives at the gap. They have their equipment on vehicles. They dismount. The first thing they do, always the first thing, is establish security. Even before a single bridge component comes off a vehicle, there are soldiers with weapons scanning the far side of the gap, the flanks, the rear. Because without security, without knowing what is around you, nothing else matters. Then the reconnaissance happens, even if it is hasty. Someone goes to the edge and looks. How wide is the gap? What is on the other side? Is the far bank accessible? Is there enemy in immediate proximity? Then the work begins. Bridge components are heavy. The panels, the transoms, the rakers, the handrail components. Moving them forward to the gap edge is physical labor under load. These are not lightweight pieces. They require multiple soldiers working together to carry and position them, and they are being moved while the soldiers are wearing full combat equipment, carrying weapons, wearing body armor, operating in a threat environment where they are scanning their surroundings even as their hands are occupied with the bridge components. The bridge grows from one bank toward the other. Each panel is connected to the last. The structure extends out over the gap as it is built, which means the soldiers working at the forward end of the bridge are progressively further from cover and more exposed the more progress they make. The last few sections before the bridge reaches the far bank are assembled at the most exposed point of the crossing, directly above the center of the gap, with nothing between the engineer and anyone on the far side except the air. Then the bridge lands. The far bank receives it. It is locked into position. Load testing is sometimes possible, sometimes not. The first vehicle crosses. That first crossing, that first tank or truck or infantry carrier rolling over a bridge that 12 soldiers just built by hand in a contested environment. That moment, the engineers who have been part of that describe it in ways that are difficult to put into adequate language. There is exhaustion, there is relief. There is a very specific pride that comes from having done something that seemed impossible and having done it anyway. And then there is the immediate practical reality that the mission is not over and there is more to do. Let us talk about the people, because equipment and doctrine and tactics are important, but the human story of combat engineering is what gives all of it meaning. The average combat engineer is young. Most enlisted engineers are in their early to mid-20s when they are doing the most demanding work of their service. They are not special operations soldiers in the way that the broader public understands that term. They are not recruited from a population of superhuman athletes. They are regular young Americans who went to engineer school, learned a technically demanding trade, and then went forward and did what their training prepared them to do, in situations that no training can fully prepare anyone for. What distinguishes them is not some exceptional physical quality, though the work certainly demands physical strength. What distinguishes them is something that is almost harder to quantify. It is a particular orientation toward problems, a refusal to accept that an obstacle is the end of the conversation, a trained instinct that says the obstacle is the mission and the mission is to defeat the obstacle, and that this is done by working, by thinking, by solving, even when the environment is doing everything possible to make working and thinking and solving feel impossible. One combat engineer who served multiple deployments in Iraq and Afghanistan described it in a way that has stayed with everyone who heard it. He said that the hardest part of building a bridge under fire is not the fire. The fire is there, it is real, it is dangerous. But you know what to do about fire. You suppress it, you avoid it, you push through it. The hardest part is the precision, because the bridge has to be right. The measurements have to be right. The connections have to be right. The bank seats have to be right. You cannot build a bridge that is almost correct. An almost correct bridge falls when the tank crosses it. And then you have a tank in the river, you have a crew dead or trapped, and the crossing fails anyway. So in the middle of everything, in the middle of the noise and the fire and the radio traffic and the casualties and the exhaustion, you still have to be precise. You still have to think. That is the real demand of the job. That is combat engineering. The fire is part of it. The precision is part of it. And the two things have to coexist because neither one is going away. Let us talk about the planning process in more detail, because the success of a bridge building operation is determined as much by what happens before the first engineer steps onto the crossing site as by what happens at the water's edge. Military engineers use a planning framework called the Military Decision-Making Process, or MDMP, like all Army units. But within that framework, engineers apply specific analytical tools for obstacle crossing. The first step is mission analysis. The engineer commander has to understand exactly what the crossing is supposed to achieve. Is this a hasty crossing, meaning an opportunistic crossing of an obstacle the force encounters during movement? Or is it a deliberate crossing, meaning a planned operation against a defended obstacle that has been reconnoitered and prepared for? The answer to that question changes almost everything about how the crossing is planned and executed. A hasty crossing is exactly what it sounds like. The force encounters a gap or a water obstacle, the engineer commander assesses the situation quickly, selects a technique, and executes with whatever assets are at hand and whatever time the tactical situation permits. Hasty crossings are dangerous because there is less information, less preparation, and less time to get everything right before the first boats go in the water or the first bridge bay hits the river. A deliberate crossing is a different animal. The enemy knows you are coming. You know they know. The crossing site has been reconnoitered. The enemy has prepared defenses. You have brought the full weight of planning and coordination to bear on the problem. Artillery fires, close air support, smoke to obscure the crossing site, engineer assets from multiple units potentially working in coordination, infantry and armor arrayed to cross as soon as the bridge is complete. Everything is synchronized to a timeline. Everything depends on everything else working. The deliberate crossing is in some ways more manageable than the hasty crossing because there is more information and more preparation. But it is also more dangerous in a specific way. The enemy has had time to prepare too. Their defenses are deeper and more organized. Their fires are more accurately registered on the crossing site, and they will fight harder to stop it because they know what is coming. The smoke is worth discussing on its own. Because one of the things that engineers and the combined arms team do to make a crossing survivable is generate massive quantities of smoke to screen the crossing site from enemy observation. Smoke generators, smoke pots, artillery-delivered smoke rounds, all of it working together to create a visual barrier between the engineers building the bridge and the enemy trying to destroy them and it. Smoke is not a perfect solution. It obscures vision in all directions, including the engineers. Working in heavy smoke is disorienting. It changes depth perception. It makes distance judgments harder, and it does not stop weapons with infrared targeting capability. But it reduces the volume and accuracy of enemy direct fire. It denies the enemy the ability to make precise adjustments to their indirect fire, and it creates a temporary window in which the engineers have a better chance of completing their work. The timing of when smoke is employed, how much is used, and where it is placed relative to the crossing site requires careful coordination. Too much smoke in the wrong place can obscure friendly forces from each other, cause friendly fire incidents, and make command and control impossible. Too little smoke and the crossing site is naked to enemy observation throughout the entire operation. There is an entire discipline within engineer planning devoted to this coordination. And the officers and non-commissioned officers who lead combat engineer units are masters of it in the way that years of training and multiple real-world deployments produce mastery. Now let us talk about the non-commissioned officers. Because in the United States Army, and in combat engineering specifically, the NCO Corps is where the institutional knowledge lives. It is where the hard lessons learned across generations of crossings, from the Rhine to the Euphrates, from the training ranges of Fort Leonard Wood to the real rivers of combat deployments. It is where all of that gets passed forward to the next generation. The combat engineer staff sergeant leading a bridge crew is typically a soldier with 8 to 12 years of service. He has built ribbons bridges in training hundreds of times. He has diagnosed equipment failures in the middle of simulated crossing operations and figured out solutions without stopping the clock. He has mentored young soldiers through the physical and mental demands of the job. And in many cases, he has done real crossings under real conditions in real theaters. That staff sergeant is the person who keeps the bridge crew functioning when the crossing site goes wrong, when the equipment malfunctions and there is no manual for the specific failure that just presented itself. When a soldier goes down and needs to be evacuated, and the crew is suddenly short-handed. When the current is stronger than the reconnaissance said it would be, and the bay sections are drifting off position, and the window for completing the bridge before first light is closing. In all of those moments, the staff sergeant is the axis around which everything else rotates. The officer, the lieutenant or captain commanding the engineer platoon or company, provides the planning, the coordination with the supported force, the decision authority on questions above the crew level. But the NCO makes the bridge happen, with his hands and his experience and his voice, and his refusal to let his crew quit when quitting would be the easier choice. This dynamic between officers and NCOs in combat engineering is one of the things that makes the community function. Neither group can succeed without the other. The officer who tries to do the NCO's job is wasting the talent of the most experienced people in his formation. The NCO who operates without effective officer support has no coordination with the supported force and no connection to the broader operational picture. Together, they form a team that is greater than the sum of its parts, which is the only kind of team that gets a bridge built in a contested crossing site before the window closes. Let us talk about the physical environment more specifically, because rivers do not cooperate with bridge building operations. They do not slow down because there is a mission on. They do not become shallow because the engineers need shallow water. They do not stop moving because the bridge erection boats need still water to hold the bay sections in position. Current is the engineer's constant adversary in a wet gap crossing. A river running at even moderate speed exerts significant force on a floating bridge structure. Each bay is essentially a pontoon, floating, connected to the others, and the current pushes on all of it simultaneously. The bridge erection boats work against that current continuously to hold the bridge in position. When a current is stronger than expected, the boats have to work harder, consuming fuel faster, increasing engine noise which can reveal position, and potentially exceeding the capability of the boats available. Water temperature matters too. Engineers working in rivers are frequently in the water themselves, either voluntarily to conduct reconnaissance or make repairs, or involuntarily when equipment fails or the situation forces them into the water. Cold water immersion is a serious risk. A soldier who goes into a cold river in full equipment can lose effective fine motor control within minutes, can become incapacitated within a short period if they are not extracted and treated. This is not an abstract concern. It is a real physical factor that engineer commanders plan around, designating water rescue personnel and positioning them accordingly. Water depth affects the bank approaches. A river that is shallow in the middle can have steep, undercut banks at the edges that make getting vehicles to and from the bridge impossible without additional work. Engineers sometimes have to excavate bank approaches, build improved access ramps using whatever material is available, or use their equipment to create a trafficable path to the bridge entry and exit points on both banks. River bottom composition affects whether vehicles can enter or exit the water directly, which matters in some crossing configurations, and it affects whether anchor stakes and bank seat equipment can be set properly to hold the bridge in place against the current. All of this is known before the operation begins. Ideally, the reconnaissance was supposed to answer these questions, but rivers change. Rain upstream can raise the water level and increase the current between the time the reconnaissance was conducted and the time the operation executes. The bank approach that looked workable at night reconnaissance can turn out to be impassable in practice when the actual equipment tries to use it. The bottom composition that felt firm under a swimmer's feet can give way under the weight of a tank trying to approach from the water. Engineers adapt. That is the consistent theme in everything they do. Whatever the plan said, reality is what it is, and the engineer finds a solution to what reality presents, rather than what the plan expected. The role of combat engineers extends beyond bridges, far beyond, but bridges are the element of their mission that most powerfully illustrates what they are and what they represent, because a bridge is visible, a bridge is tangible. A bridge is something you can point to and say, that was not there before, and now it is. And because of it, something changed. Minefields cleared are invisible after the clearing. Obstacles demolished become absence rather than presence. But a bridge stands. It connects two points that were separated. It makes possible what was impossible. And for the soldiers crossing it under fire, toward an objective that matters, it is the most important structure on Earth in that moment. There are engineer soldiers who have built bridges under fire and have never talked about it publicly, who went back to garrison or back home and continued living regular lives without anyone around them knowing what they did. Their neighbors do not know. Their families sometimes know only the outline, not the detail. The co-workers they worked alongside after leaving the service have no idea. This is true of a great deal of what the military does. The work happens in places most Americans will never go, in conditions most Americans will never face, for reasons that most Americans will never fully understand, because the context requires more than a news article to convey. And the people who do the work generally do not insist on recognition. They went forward because the mission required it. They built the bridge because the infantry needed it. They got back in the boat because there was no one else to get in the boat, and then they came home and they were quiet about it. If you know someone who served as a combat engineer, take a moment to recognize what that actually means. Not just the general idea of military service, which is worthy of respect on its own, but the specific reality of that job. The water, the weight, the fire, the precision under impossible conditions. The bridge that got done because the engineer refused to let it not get done. Let us go deeper into the tactical context of a major crossing operation, because understanding the coordination involved helps explain why the engineer's role is so critical and so dangerous. In a deliberate river crossing, the operation has three phases that operate in sequence and then overlap. The first phase is the far bank fight. Infantry and assault boats, supported by everything the combined arms team can bring to bear, crosses to the far bank and begins fighting to expand the beachhead. This is the most dangerous phase for the infantry because they are exposed, they have minimal vehicle support, they are fighting in close terrain against a prepared enemy, and their only lifeline is the boats bringing more soldiers and the fires coming from the near bank and from overhead. The engineers running those assault boats are in the water throughout this phase, driving back and forth, taking fire, keeping the lifeline open. The second phase is the gap crossing itself. The bridge goes in. Engineer crews work in the water, in the fire, under smoke, against the current, building the structure that the rest of the force will use to cross. This is the phase we have spent most of our time discussing. It is the phase that most visibly belongs to the engineer. The third phase is the buildup. Once the bridge is complete, vehicles begin crossing in sequence. Armor, artillery, logistics elements, command and control vehicles, medical assets. The crossing site becomes a traffic control problem as much as an engineering problem. Engineers control the bridge, manage the traffic, monitor the structure's condition under load, and maintain the bridging equipment against the current and the wear of continuous vehicle crossings. Throughout all three phases, the enemy is doing everything possible to disrupt the crossing. In the first phase, they are fighting the infantry on the far bank and firing on the assault boats. In the second phase, they are targeting the bridge construction with every asset available. In the third phase, when the bridge is complete and vehicles are crossing, the bridge becomes an even more attractive target, because destroying it when it is full of vehicles, or after a significant force has crossed, but before the entire force is across, splits the force across the river and can produce a catastrophic operational failure. The engineers responsible for the bridge during the third phase are therefore not in a less dangerous situation than they were during the second phase. The threat is different in character, but not necessarily lower in intensity. Air attacks, artillery, long-range anti-tank missiles, all of it is potentially directed at the bridge while vehicles are crossing. And if the bridge is damaged, the engineer's job is to repair it, immediately, while traffic is stopped, while additional rounds are coming in, while the commander is demanding to know when the crossing will resume. This is why engineer units train with such intensity on bridge maintenance and repair, because a bridge that is 90% functional after enemy fire is not functional at all if it cannot carry tanks. Every component matters. Every connection point matters. The ability to diagnose what is wrong with a damaged bridge structure, identify what repair is possible given the materials available, execute that repair in minimum time under fire, and get traffic moving again. That capability is the difference between a crossing that succeeds and a force that is split across a river and destroyed in detail. The modern battlefield has added complications that previous generations of combat engineers did not face in the same way. Unmanned aerial systems, drones, have fundamentally changed the reconnaissance problem for both sides. An enemy with drone capability can monitor a crossing site continuously, observe the engineer's preparations in real time, adjust fires with precision, and strike at the most vulnerable moments of the crossing operation. The bridge erection boat carriers driving toward the water are visible. The engineer crews working on the bridge are visible. The bridge itself is visible. This means that the traditional smoke screens that engineers have relied on for concealment are now insufficient against an enemy with thermal imaging drones that can see through smoke. Modern engineer units have to account for the drone threat in a way that changes how they operate, when they operate, how they approach the crossing site, and how they manage their signature. Operating at night has always been preferred for crossing operations because it reduces the enemy's ability to observe and accurately engage the crossing site. Night crossings are harder for the engineers because the work is harder in the dark, navigation is harder, equipment management is harder, and coordination is harder. But those difficulties are accepted because the reduced enemy observation during night operations generally makes the crossing more survivable. The drone threat has made night operations more complex because thermal imaging capability removes much of the advantage that darkness previously provided. An enemy with thermal drones can observe engineers at night almost as effectively as during daylight. This has pushed the conversation toward other mitigation strategies, including electronic countermeasures to interfere with drone communications and control, faster execution to reduce the time spent exposed at the crossing site, and more aggressive counter-drone operations conducted in coordination with other elements of the combined arms team. This is how military engineering evolves. The threat changes and the engineers adapt. The fundamental problem has not changed since Caesar bridged the Rhine, and the fundamentals of the solution have not changed either. Get across the obstacle, do it faster than the enemy can stop you, and be ready to fight while you are doing it. The technology changes, the principle does not. Let us talk about training. Because everything we have described, all of the capability, all of the performance under fire, all of the precision in impossible conditions, it comes from training. And the training that combat engineers go through is designed to simulate the real crossing environment as closely as peacetime safety constraints allow. At the Army's combat training centers, the Joint Readiness Training Center at Fort Johnson in Louisiana and the National Training Center at Fort Irwin in California, engineer units go through rotations that test their crossing capability against simulated enemy forces using sophisticated instrumented systems to track performance and replicate the chaos and pressure of real combat. These rotations are designed to be hard in specific ways. The enemy force, the opposing force or OPFOR, knows the engineers are coming. They have prepared defenses. They will hit the crossing site at the worst possible moment. Equipment will fail at inconvenient times. Key leaders will be taken out of the scenario to force subordinates to step up and carry the mission. The crossing window will be tighter than planned. The intelligence picture will be wrong about something important. All of the ways that real crossings go wrong are deliberately replicated so that when real crossings have to happen, the engineers have already been there. Not exactly, not in every detail, but close enough that nothing completely surprises them. The river crossings at training centers are conducted on real water, real rivers and lakes, with real bridge equipment, under real-time pressure, with real observer controllers, watching and documenting every decision and every action. An engineer unit that performs poorly in a crossing training rotation goes home with a detailed picture of exactly how and why they failed, and what they need to fix before the next rotation or before deployment. There is a culture in the combat engineer community of learning from failure that is not universal across all military units. It exists because the consequences of failure in a real crossing are so extreme and so visible that the instinct to understand failure and prevent its recurrence is deeply embedded in how engineers talk about their work. After every major training exercise, there is an after-action review, the AAR, where leaders and soldiers alike sit down and go through what happened. What the plan said would happen, what actually happened, why the gap between plan and reality existed, and what specific actions will close that gap before the next time. This process happens in training,